Hello, comrades. Greetings to all. We are glad to welcome you again to our studio. Today we have Sasha Mironov with us, so we're going to talk about what's inside airplanes. Last time we talked about something like the engine. This time we are talking about systems. Well, the engine is a kind of system, but it is probably the biggest system in the airplane, the biggest there can be. But besides that, there are many other different things. This is what we are going to discuss because in our new project there are quite a few changes and improvements in terms of modeling internal processes, let's say, so in the airplane, because an airplane is not just an airframe, it's not just an engine. No? It's also a bunch of different systems that control the different elements of the airplane. So what types do we have now? Sasha will tell us. Go ahead.
Well, if we go way back in history, there weren't that many systems in rise of flight. There was the engine system, the oil system, and the cooling system. Well, also the fuel system. Let's say they were in a more basic stage. On these systems, I think the fuel, the oil, and the engine cooling systems so were transferred to new projects. They certainly became more complex, and some elements like thermostats were added. But overall, we basically didn't have any other systems. As aircraft became more complex, they needed to behave and respond appropriately to certain types of damage. But they did. That's the main point, let's say. That is damage to the aircraft and damage to some of the systems. It's not just like two states, aircraft flying or crashing. To achieve this diversity, we started to introduce not complete systems, but let's say proto-systems. We had some beginnings with our very first Great Battles aircraft, and now it was necessary to create not only these proto-systems, but more complex systems. To implement it and to do it in such a way that it serves as a kind of skeleton, a framework, on top of which we will later complicate these systems, add elements, possibly do more detailed modeling. But from a technological point of view, we had to create a framework. That framework was created. And the first systems have already been made based on it. These are the hydraulic system, the pneumatic system, and the electrical system.
All right, good. So let's briefly describe what each of them is responsible for.
All right, so let's start with the electrical system. The airplane has a lot of instruments. The airplane has components such as the engine starter, all of which require electricity for these elements to work properly. To keep the player interested, wow, the light bulb turned on or off. So we created an electrical system, not in the way where an engine starts and power variable is automatically set to true. From the perspective of the new system, these are the components. Power source, such as a generator or battery, which can be damaged separately. Consumer, and it can also be damaged separately. And this is the main thing, to the connections, in this case, the wires between these elements, which can also be damaged and affect a specific consumer or a group of consumers. Or if this is the only wire, so to speak, from the generator, then the whole system shuts down.
Is the power system implemented as some kind of logical network, or does it have parameters like voltage, etc.?
The system is now designed in such a way that it can be made in its simplest form as a set of logic.
Well, on-off.
Yes, on-off. It's very convenient for AI aircraft, so they don't have to model the whole system with currents, voltages, voltage drops, ohms and Kirchhoff's laws, and so on. The same goes for real voltages with real consumption currents, with actual consumption corresponding to the load on the power source, so on the generator. Voltage drop, light bulbs can dim when there is insufficient power supply.
And we will have that?
Yes, we will.
Wow. Well, let's probably talk about everything. It might take too long. Let's talk about the fuel system. People might still be interested in that. Yeah.
Oh, so you want me to talk about
how it's going to be implemented in Korea, because it's a long story for us.
It's a very old story indeed. The fuel system needed improvement a long time ago. We've finally gotten there. The tank structure will be made more complex. They may be introduced. We'll see how much control we want to give the user. Additional valves will be introduced to transfer fuel from tank to tank, so that if a fuel line from any tank is damaged, it can be isolated and drawn from another tank. Let's call it fuel management. But at pumping fuel, We didn't have that feature yet. So there are external tanks that can be dropped.
Oh, well, we don't have a vodka refill station yet. Well, in this case, we have enough
Yes,
new
but
things
the
already.
innovations are certainly enough for now. That's for sure.
Also, there is a point where the new engine, the jet engine, will have some kind of fuel system. And we also plan to damage that equipment. They are almost ready, but with the introduction of the system, it just needs to be put together.
Here we have a little topic we want to discuss with you. It's modeling versus animation. So there is the approach that we used a lot at Great Battles, especially with the starting of the aircraft, when your start process matches what it should have been, according to the flight operations manual, but it was largely an animation. For it not to be an animation, it needed systems. So what is the benefit of modeling a detailed system in that sense?
Detailed modeling leads to some features that happen naturally in life will happen naturally in the game. That is, there will be no need to program it separately. Let's talk about the Mustang's hydraulic system. It had this special feature, the inner landing gear doors, which are attached to the fuselage, not to the landing gear. And the flaps, they are operated by the hydraulic system. But when the airplane is shutting down, the pilot has to release the pressure from the hydraulic system. And these landing gear doors and flaps gently move under their own weight. They are released because there is no pressure, and they move down. And accordingly, when the engine of the airplane starts, the pressure in the hydraulic system increases, and they rise by themselves. So such a feature, if the hydraulic system is modeled honestly, such a feature does not need to be programmed in advance. It will happen by itself.
Right, but how are we supposed to see all these systems at work while sitting in the plane's cockpit?
We have devices for that. The devices are also planned to have extended functionality. That is, it is not just a simple pointer drone that moves depending on pressure or voltage and current. The device will be considered as a more complex object that can live its own life. Let's say its arrows will vibrate. Everybody has seen various videos on YouTube where the airplane is going down the runway and the joints of the panels,
All panel joints, his entire dashboard is like
doing
this.
shaking and vibrating. And the arrows are all over the place. For all this to work, it was necessary to complicate the instrumentation. They are also devices that are connected to systems. They have their own power supply. Or if it is a device that shows something directly related to the hydraulic system or pneumatic, it will have its own pressure that is present in the system. In general, the device will be more complex, more interesting. Or let's say an air pressure sensor. It would be very good to model it in terms of inaccuracies, for example.
Let's first explain what this is and why it's needed. Not
In an
everyone
airplane,
knows.
the most important instrument is the Tamer speed indicator. The pilot must know the speed at which he is flying to ensure that the airplane does not stall or spin. However, this instrument is tricky because it has a margin of error, and that error depends on the speed, specifically the angle of attack. It's important to note that different planes, they will have different margins of error. Usually because of this, the training plan is then adjusted to the aircraft. And so when we model this device more accurately, we can then use this training plan to help our airplane hit the references more accurately.
We're going to talk about how we see the evolution of this whole story as it relates to the systems.
Well, I think that, let's say, a lot of users like to fiddle with different knobs and buttons. And if we complicate the systems, we can create more so-called controls. And to switch things, turn something on, see how the system reacts and say, wow, it works. That is to increase the interest of those users who want to see more of a cockpit simulator than just a game.
But at the same time, I hope he's,
Yes, the main
I hope
thing
that we don't make
here
life
is
more difficult for
to,
people who want to see the game.
to keep the balance so that everyone likes it, not to go into too much detail.
Regarding the fuel system, probably an additional question. For example, will the player be able to control whether fuel is consumed from the external or internal tanks?
Yes, of course. We are going to give the player the ability to turn these fuel valves, and not just the ones that are turned off because there is no fuel, but to actually choose the tank. We're going to have consumption from, say, the left wing tank, not the right wing tank.
We definitely have a lot of features planned, but will we make it in time?
Well, let's just say that about half of it is already done on our end.
Well, okay. In terms of that, since we have a little bit of time, let's talk a little bit about combat damage. For example, let's take the hydraulic system, right? How will the aircraft behave? Everything that has to do with its operation, the operation of its hydraulic system in the event of, let's say, a puncture in the fuel hydraulic line.
Well, most likely, if its flaps were down and we damaged the line that deployed and retracted them, then the airflow would probably retract them to some degree. So now we might have some problems during the landing. If we have broken the main line responsible for landing gear retraction, then of course the gear will not be retracted by the hydraulic system. However, they have a feature, and this is already implemented in some aircraft, which is that if the landing gear is not locked in the retracted position, it will just fall down. If there's enough force, let's say the energy of the landing gear falling out to lock into the deployed position, then they will lock. And if there is not enough, then they won't lock. And you could have even more problems landing.
And if we can shake the plane, can it help?
Of course, we can shake, roll, wiggle, and the landing gear will lock, and all will be well.
Regarding landing gear deployment, we are sure to be asked, will there be an emergency release?
Yes, I think we're going to do an emergency release, but I don't know if it's going to help from a hydraulic system perspective if we have, for example, a single line that's broken and we can't do anything about it. Whereas there are aircraft that have an emergency release implemented with, for example, a pneumatic system.
Yes, if you blow air into the hydraulic cylinder.
And even if there is damage, it could save us because there is a reserve of air and the pressure is also given with a reserve.
All right, dear comrades, let's move on to the second part of our meeting today, which is devoted to your questions. Thank you very much for sending and asking these questions. As I always like to say, we are very interested in reading and answering them. In fact, the answers to these questions sometimes make up a large part of our episodes. So you largely determine what we actually talk about here. Well, let's start with this. Looking back on everything you have worked on and implemented so far, what would you say was the most challenging and time-consuming part of working on all these various sorts of systems?
My favorite question. The hardest part of development, whether it's a system or an engine, is knowing when to stop. You have to be able to restrain yourself so that you don't get bogged down in details that take a mind-boggling amount of time to implement. But the result, the outcome, is only going to be seen by one or two persons in the community. Of course, the balance of effort and resources spent on development and results should be maintained. Maintaining this balance is the most difficult part.
I agree. As a project manager, I agree. The next question, we partly answered it, and partly it relates to the topic of the next lecture, which we will have on damage systems, but still when we talk about the aircraft systems, it's always about the damage because, as you said, the systems are created primarily to be damaged. It's always interesting to know what's going on. Here's one such question. Will there be damage to the hydraulic and pneumatic strut system? The answer was yes, there will be. Asymmetrically deployed flaps.
Well, you have to understand that if it's mechanically designed so that the flaps are mounted on a single axis and that axis is driven by a hydraulic or pneumatic cylinder, then asymmetric deployment cannot occur in this case unless we physically damage, well, that drive shaft itself. But then the question is, can we deploy one section, either the left or the right, while the other remains hanging in the air? Yes, we can.
And here you have to understand that in modern aviation, when it comes to fighter aviation, there are so-called flaperons. And they should be controlled separately, so each wing is equipped with a separate drive. But in the aviation of that time, the most common scheme was when the flap drive was hanging. It hangs on a shaft from both sides. One drive turns the worm mechanism which turns the shaft that goes to both wings. And even if you're flying in a commercial airplane and you hear the flaps open with a loud noise, why do you hear that? Because the flap mechanism is not in the wing, but in the fuselage underneath you. It's one mechanism for both sides, so it's pretty big and powerful. I've held one in my hands. In fact, I couldn't hold it in my hands. The flap actuator of the 2160. No, I don't think it was the 2160. I think it was another, the IL-76. Well, it's like this thing, half the size of a room. Next, the brakes that can fail during the run.
Oh, what an interesting topic we have here. I don't know if it was mentioned or not, but our wheels will be damageable. Yes, it's in the same category. Well, brakes, if you look at the hydraulic braking system, are a thing of their own. They are usually completely separate in an airplane, just so that nothing affects them, the hydraulic brake system. But the pneumatic system, yes, if we don't have air, the wheels just won't brake.
Uh-huh. All right, so the next question is a bit away from the main systems, but the radio system is also important. Will there be radio beacons in Korea? NDB or non-directional beacons. Will the player be able to control the radio compass frequencies by switching between beacons?
Right now we have a concept like the frequency of a radio beacon. And radio equipment can, in principle, use beacons on different frequencies. This is already a gameplay question. Will we allow the player to adjust something extra or not? If we allow it, then yes, please, let's work with it.
Yeah, I talked to Roman recently. He said, you will allow it. We will.
It seems like the question was about additional options to control the instruments.
Right now, there are also radio beacons in great battles, but they are automatically tuned to the nearest beacon, so as not to introduce additional controls, so as not to confuse our users. But since in Korea we plan to significantly simplify the player's understanding of the current control settings and what to press, you will have a so-called radial menu. And through this radial menu, he will be able to control any system of the plane without too much hassle, yes, without using his memory, and he doesn't have to remember a billion buttons or have such a big, an input map, a command map chart. Now you can work with it because some commands can be left without default key bindings and still be managed. By the way, dear comrades, this is strangely enough one of the results of our work on connectivity and support for devices like GamePads. An unexpected story like this is that when we worked on controlling the plane with seemingly simplified devices, it led to a significant improvement in quality of life and gameplay for players using a standard set of devices. Well, on the other hand, when it comes to this sort of thing, it always seems to happen to us. As you know, we always try to make everything we do as universal as possible for all of our players, which is why such a story is possible to tell here. All right, moving on. Okay, so we just answered this question. All right, so here's the question. Now, how will the roll control of the airplane, if it has hydraulic boosters, be affected if the hydraulic system fails?
So that's actually a very good question. Yes. A lot of our users don't know that we have hydraulic boosters modeled on a current aircraft in the Great Battles series, the P-38.
Lightning?
Yes, in fact, the ailerons are controlled by hydraulic boosters.
These boosters, you can't just turn them off. Each hydraulic pump engine has two sources of power, and if one doesn't work, our performance drops accordingly. I may be a little off. I haven't studied the flight manual for the P-38, but I think if the hydraulic booster is just forcibly shut down, the controls get heavier.
How does it manifest
itself in the fact
itself?
that we have less control over the airplane at high speeds. The pilot doesn't have enough strength in his arms to deflect the ailerons to the angle that they are deflected with the help of hydraulic boosters. And that is now part of the game already in Great Battles. Though they will just be more developed. We're not just going to have an engine failure that causes this. Damage to the line, damage to the booster itself will cause it, not something like that.
As mentioned earlier, in the physical models, we add the appropriate elements. Huh? For example, the same hydraulic aileron booster
Yes,
will
wiring
have a
would also
corresponding
have
physical element there.
its own some physical representation. By the way, the control wiring is just cables and rods, so this is progress for us as well.
Will the modeling of the breaking and destruction of the rods and levers of the control channels be simulated? This question is sort of for our next dev brief, but since we're talking about control, let's answer it.
that. Yes, we are already working on, let's say, a more detailed damage model in terms of adding these collisions of rods, levers, cables, so that it's not just hitting somewhere there, leading to a control failure, for example, but rather a specific place, characteristic place for each plane. I mean, well, that's a question of content, but still, it turns out to be such an improvement.
It's important to say that even in great battles, there was interference in the rods and levers. In the control channels, yes, it is there, just like I said before. Statistically, it works. If you hit the part of the wing where the control wires run, then with some probability, depending on the angle of impact, the wires will be damaged and the aileron starts to wobble. In Korea, the main difference in this sense will be that a separate collision object will be created for the control wiring. That is a specific section that must be hit directly.
There can be several sections.
All right, next question. How would you describe the evolution of approaches to modeling all the various aircraft systems, starting with our first title, Rise of Flight, and then through all the titles of the Great Battles series, and now with Korea?
I would say that in Rise of Flight, there were some rudimentary systems. There were very few. They were not connected, and they were scattered. They were just animations, so to speak, of the necessary devices. In the Great Battles series of titles, as the airplanes became more complex, more detailed systems were required. And with each airplane, as those systems became more and more complicated, we had to come up with new and new ways to somehow do it. But again, without much systematicity, let's say. And now in Korea, we have finally reached the point where we have created a unified and organized system. Excuse the tautology, the integrated system, how to build such systems, how to easily string a chain of a large number of elements, create a complex system that can be controlled, in which individual elements can be damaged, the connections between these elements, and so on. So we are getting, let's say, we are getting a substantial qualitative leap in the development of the foundation. And the development of this foundation, it allows us to create such complex systems.
Well, basically, when we started with Korea, our main idea was to develop and make a step in all the major technologies that we have in the game. Not only the aircraft and the graphics, but also the game world and, of course, the aircraft. Well, okay, let's go to the last question. And what happens if the fuel automation of the jet engine is damaged? That's the question.
Wow, that's a good one. It turns out that our jet engine is regulated only by the amount of fuel, well, roughly speaking, only by the amount of fuel that is actually delivered to the combustion chamber. So what can we do? We can either cut off the fuel supply completely and then our engine will just shut down. Or we can break the flow regulator. The pressure is actually regulated, so the flow of fuel going into the combustion chambers is regulated. In this way, the amount of fuel is automatically adjusted depending on speed and altitude. And the fuel regulator failure will lead to the fact that we may exceed the permissible engine speed, or conversely, with increasing speed, we may not have enough fuel, for example, and our thrust will decrease. All of this will require the player to manually adjust the position of the throttle, and he will certainly need to keep a close eye on the instruments to avoid a breakdown.
And to
Yes.
overfuel it so that it can catch fire. Can we do that in this case?
Most likely what's going to happen here is that if this automation is damaged, the fuel will just flow somewhere over there, in that direction, and it will catch fire a lot faster than we can think of such a possibility.
Okay, Sasha, thank you very much for visiting us today and telling us all about all of this. Very interesting, although it's a very complex topic. And with that, dear viewers, please make sure you subscribe to our channel and keep up with the updates and subscribe to our social media. We are on X, we are on Facebook and YouTube, and we are even on Telegram and Reddit. We are everywhere, so please subscribe and like this video if you liked it. leave a comment, ask questions. And throughout the week, we will keep an eye on the comments on the video, and I will probably even answer some of the questions. That's it. Thank you very much. Goodbye, comrades.